Alright, hi everyone, welcome to my YouTube channel, City of Electrons. So in this video, we are going to talk about this guy here. Okay, now looking at this particular thing, this is an antenna. Okay, an example of antenna. Example, just one example. There are different kinds of antenna. There are antennas that do not have such a bowl or plates or surface area. However, there is need to understand or to know the form of waves that is being what related from this antenna or from the surface of this antenna. Okay, the forms of wave. When we say forms of wave, we are referring to forms of wave. When we say forms of waves or form of waves, we are saying that what what is the intensity of the wave, or what is the direction of the wave, or properties or characteristics of the wave that is related from this antenna. When we say wave here, we mean what? Electromagnetic wave. Okay, so then looking at the first thing that was done in class, the first sentence, okay, or statement. Now we may determine the forms. I just talked about forms of waves, meaning the characteristics of a wave. Okay, knowing the characteristics will help us to work with that particular wave or antenna properly, efficiently. So the wave is going in which direction, what is the intensity, and things like that. Okay, so how to determine them? We may determine the forms of wave related from an antenna. How? If we know what? If we know distribution, if we know the current distribution over the surface of the antenna. What do we mean by current distribution? Back to this guy. Now, current distribution simply means the flow of current over the surface of the antenna. It must not necessarily be only surface, okay? But any part of the antenna producing, or where you have a current flowing, let me use the word flowing instead of producing. So any part of the antenna where you have current flowing, that part contributes to the entire current distribution, contribute to the entire flow of currents, okay, of that antenna. And we know alternating currents will do what? Once we have alternating currents, field is generated, magnetic field is generated. So that magnetic field generated, a changing magnetic field produces what? An electric field. So our current, the way current is distributed over the antenna, this will affect the electric and magnetic field. And of course, electric and magnetic field, they propagate themselves through space. So if we know the current distribution over the surface of the antenna, what are we going to do with that? We may be able to determine the forms of waves. Characteristics of wave. Okay, so let me just read that one more time. Let me read it one more time. Okay, we may determine the forms of waves related from an antenna if we know the current distribution over the surface of the antenna. I hope that's clear. Pause the video, take it back if you have to. Okay, so leave questions in the comment section. Okay, so you get this thing. Now, this is just the first part of the notes that was done in class. We had about 8 pages. My handwritings are kind of large, though not too large, but we had about 8 pages, and I'm just dealing with the first page. Okay, if that's part of the first page. Okay, because if you understand this first page, it will really help in the next page. Okay, in the rest pages, it's just like addition. So this is kind of the starting point. All right, now with this being said or explained, the next thing that was said in class is this: to show this, people of electrical electronics, to show this, what is the this here? This is talking about what we just explained. Are we together? To show this, meaning to show that we may determine forms of waves related from antenna if we know the current distribution over the surface of the antenna. To show this, we first do what? Perform some preliminary vector manipulations. Why? 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 Remember, electric fields are vectors. Vectors are quantities that have what? Magnitude and direction. Electric field, magnetic field, they all have magnitude and what? Direction. So, to be able to deal with things that has to do with electromagnetic waves, and to confirm or to show that this first statement here is true, to show that, we are going to start with what? Performing preliminary vector manipulations, because we are dealing with vectors, electric and what? Magnetic field. Okay, so we first perform those manipulations, and then what? We assume, now, to perform this manipulation, listen carefully. To perform this manipulation, we have to what? Assume free space. Why are we even assuming free space? Why don't we assume something else? Why this assumption? Now, the reason is this. If you want to do something for a start or test something, okay, you want to test something, you will have to focus on that particular thing. Let's say you want to okay, let me just make things easy. Look at this now. Let's say this is space, okay? We want to walk inside this space now. Now, to reason the electromagnetic wave inside this space now, we are going to, if we want to consider some factors, okay, in space, those factors will affect the wave. Is that not so? If we consider other factors, wave in space is affected by other factors. But if we want to focus on only the wave, how the wave behaves, we have to do what? Stop thinking about other factors for simplicity. Stop thinking about other factors. Let us just focus on only the wave. So therefore, our assumption is what? On free space for simplicity. Do we get it? So this assumption is what? An intelligent assumption. All right. So we assume what? Free space. All right. And then what do? We write Maxwell's coil equations for sinusoidal field. Let's take it gradually. We write what? Maxwell's coil equation. Remember, Maxwell has what? How many equations? 4. Okay, Maxwell has 4 equations. But out of those 4 equations, we are dealing with just what? Dealing with just 2 for a start. And because we are talking about what? Waves, okay? We are dealing with just 2. And the 2 we are dealing with are the what? Coil. The coil equations. I will drop a video on the 4 Maxwell's equation. Okay, that video is here already from last semester. But remember this, we have I'll just drop you a link to that video so that I don't repeat the whole thing there again. But these are the 2 equations, 2 coil equations. The other 2 are divergence, electric field, okay, and then magnetic flux density. Okay, so but you can also use the magnetic field intensity, electric field intensity, magnetic field intensity. Okay, then this is for what? Electric flux density is for magnetic flux density. I said this in that video, so I'll just post that video also. All right, now we are picking these 2 equations. Why? We pick these 2 equations for Maxwell, right? Maxwell's coil equations. Now look at it. When you look at this equation, you see this equation what? generates what? The coil of an electric field gives us what? A changing what? Magnetic field. Now we are supposed to write this thing as what? We are supposed to write this thing as coil of electric field gives us what? Changing magnetic field. This is what we are supposed to write to. This is exactly what we are supposed to write. Oh, pardon me. We stated something that magnetic flux density is equal to what? Magnetic field intensity multiplied by how this thing responds to space. So this is for magnetic flux density. So anywhere you see this, you should write this, or anywhere you see this, you can write this. Normally, we are supposed to have this one here. We are supposed to have this one here. Okay? Coil of an electric field gives us what? Changing magnetic field in the opposite direction. That's the minus sign. Changing magnetic field. However, you can remove the magnetic field and put what? Sorry, you can remove the... What did I just say? This magnetic flux density. This is magnetic field. So, you can remove the magnetic flux density and substitute in what? This guy, which will now give you what? This. Okay? Now, there is something that was stated in this case now, saying we assume free space, yes, and write Maxwell's coil equations for what? Sinusoidal field variation. Sinusoidal. So that sinusoidal tells you that it's dealing with what? Frequency domain. So everything, look at this guy. This thing you have here, okay, this is in time domain. Write this thing in frequency domain, it will be what? J omega. Exactly. So meaning you will now have it like this. You will now have this one, look at it here, right here. Minus sign, minus sign. Partial t. It's now what? J omega. Look at it here. J omega. Then for this, permeability, and then what? Magnetic field intensity. Look at it here. Exactly. Then for this other one, coil of a magnetic field is what? Partial. Okay, J omega is simple as this one now. Okay, and then you have what? The electric field and how it responds to it, which is what? Permittivity. Okay, this one is permeability, this one is permittivity, or free space. This not means free space, plus what? The current density. Okay, that means how dense the density of the current in different areas. Okay, different density of the current in different areas, surface. Okay, so what we have here is this, or should I have to write this one? It's just like what I did to this first one. That's what we have here. Okay, so the same idea goes here. This one, it's the same thing as saying what? Partial what? Everything here. I hope that's clear. So plus what? Current density. Okay, so we'll continue from here in the next video. All right, so that'll be all for now. Thanks for watching, and like, share, subscribe, comment, and I'll see you in the next video. Bye for now.